So first of all, we got to figure out if this student is onto something or really not so much. So shall we vote? Is that okay? Raise your hand if you agree with the student. That makes sense. Sure, it sounds good. Raise your hand if you think that the student needs to check their physics. Okay, I see lots of hands for student needs to check their physics. So then the question says, what, if anything, is wrong with that statement? So tell me, what's wrong with the statement? If you think it's wrong, we got to know why, not just they don't make any sense. Chris, you going to get us started?
The change in velocity wasn't 4 meters per second because it's going 3 meters per second right to start, and it's going 7 meters per second left to end, so the change in velocity is 10 meters per second.
So initial velocity is 3 meters per second, and so you're saying that the final velocity was what? -7 meters per second. And so the change in velocity is final minus initial, so that's -7 minus 3 gives us. Does that make sense?
You're frozen.
Oh, I'm frozen, so you can't see all of the beautiful pink I've written? There you go. Thank you. I appreciate you. So I just do my own thing. I'm just listening. I'm playing the game. All right. Yeah? Okay, so then if they're wrong, then what do we need to fix it? So how does that change the story? Change in momentum, and also the impulse would be -20? Where are you getting -20 from? Mass times change in velocity is -20, so that was -10 meters per second times, that was what, 2 kilogram mass or something like that? Okay, so that gives us -20, and we need some units, don't we? Yeah, what are the units going to be? Kilogram meter per second or Newton seconds. Either one's okay, yeah? NS, yep, N times S, NS. Yeah. Life is good? Okay, sweet. So this is the big thing that I wanted to make sure we're like good with. I am going to give you, I've got 3 AP workbook pages that I want to work through as much of as we can today. That's gonna be like my primary chunk of things, okay? There are some specific things that we will go through in them, but I want to just give you a couple minutes to start. Does that sound okay? So I've got them here. I copied them on yellow paper because that seemed like the next color in the rainbow of AP workbook pages. We had pink and then we had like that bright orangish color. So I copied them on that, and then I was really trying to be a nice teacher and 3-hole punch them, and then some of them got double 3-hole punch. So it's like you could put it in either way. So I apologize for that. If that's going to drive you absolutely bananas, you know who you are, and I know that there are maybe some of you in here that just don't take the top copies. Does that make sense? So there are 3 pages, 1, 2, 3. You need to take 3 pages and that's your set. Okay? So come on up and get them and then start taking a look at 5B. Does that make sense? Come on up. Is that going to drive you nuts?
No.
Okay, then take it. That's fine. Sorry about the double holes, friends. I was trying to be good and it, sometimes that backfires on you.
Oh, yeah,
Actually, no, you shot party up again. All right. So the first thing, one of the reasons that I do like these a lot is because it uses the language that AP uses. And sometimes I use that language and sometimes I get a little lazy and just kind of get into my own little vocabulary, and it doesn't use exactly the same stuff. So I like part A because it says to identify the box system. So you might want to like highlight that or make a little note by that, because I don't know if we've really talked about the system before. Have we talked about a system officially before? Yes, no, yes. If we haven't, we are going to now. And if we have, then good for us. What did you circle in box 1 for the system? Did you circle anything? Yeah, so what did you circled the box? Yeah, you're looking at me like I'm nuts. I'm not sure if that's because I'm boring you or because I'm confusing you. Where are we at? The box? Yeah. So the thing to pay attention to here is that we're not worried about the person and we're not worried about the floor. The thing we care about in the system is just the box. Okay? The free body diagram that we're drawing is just of the box. Okay? All right, so you're going to draw those free body diagrams. What kind of forces did you have on those free body diagrams? Go, Bo, get us started.
Gravity.
You had gravity. Okay, oops. Force of the earth on the box or force of gravity that one, I'm assuming pulled down. Yeah? Okay, so we're going to go something like this. The force of the earth on the box. We put FG in parentheses. Okay? What else? We're talking about box 1 over here. Normal force. Which way does that one go? Up. How does it compare in length to this one? Same. How do you know that they're the same? It's not that it's not moving. It's that it's not accelerating, right? So we go 1, 2. I drew mine 3.5, so I'm going to go 3.5 up. 1, 2. I think that's about the same. The force of the what? What do we say? Force of surface on the box. Fn. Anything else acting? Yes. What else is acting, Shushma? Person. Which way are they pushing? That way. So I'm going to draw a force like this. The force of the person on the box. Fa. All right, I'm not going to do the other one, but tell me, how does this one compare to that one? How do the free body diagrams compare? Same? Say again? How much less? It should be a third as long. So you actually, when they put it on this nice graph paper for you, then you should use the graph paper, right? So if you made this one 9, then this one should be 3. Okay, so that second force, that second applied force is going to be really small. Fa. And again, a third as long. Talk to me about the gravity and normal forces. Do they both exist? Yes? As they were in the other one? Yeah. So in mine it was like 3, so I'm going to make those like 6. Right? I'm not actually counting, but you get the idea. So this is going to be twice as big, Fg, and twice as big up, Fn. We doing okay? Okay. That's not unit 3 stuff. That's just stuff that we need to know. We need to make sure. The forces that are external to the system, that means that things are not inside. What does that mean? We'll talk about it in a minute. What did you include? Just going to list them, right? Normal force, gravitational force, applied force. Okay. Sweet. All right. Part C says, sketch a graph of the net external force versus time for each box. How'd we do? How do you do it? What are you doing? It says sketch. Sketch means no numbers. You might want to make yourself a note there. Sketch means that you don't have to have numbers. No values. But you need to have things relatively sized. What does it look like? 2 parallel lines. What's the slope of each of those parallel lines, friends? 0. So there's one like here. I think this one's going to be for box 2 because I think I'm just trying to color code there. So my box 1 force, is it going to be above or below? Above, because it's 3 times as big, right? So I actually needed to count. I didn't actually count, but I'm going to pretend like that's 3 times as big. Okay, it's supposed to be a horizontal line for box 2. Okay, you can also use dotted lines and thick lines or whatever to differentiate. We doing okay? Everybody's... Oh, yeah, thank you. Next one, thanks. True statement. We doing okay so far? Everybody's happy? Sweet. All right, qualitative analysis part D says, using the equation for the area of a rectangle, write 2 equations, one with words, one with units. Oh, we've done this before, haven't we? The area between the net external force versus timeline and the x-axis gives you what? What does that tell you? Let's just do this part here. The area is what? Represents the what? The newtons times seconds. What is newtons times seconds? The impulse or you could say and the what? Change in momentum. Everybody happy? Everybody good? Yay! Then we go to the back. We go to some funky graphs. Did you get to the back yet? Have you looked at it? Oh, they're kind of weird. Let's take a look at them together for a couple minutes here. Re-represent the data by creating a momentum diagram for each box on the same set of axes by using 2 different colors. Or you can do, dotted lines and whatever. We can figure that out, okay? If you have lots of colors in your pencil bag, then go for it, okay? A momentum diagram represents the momentum of an object or system by showing the mass of the object as the width on the bar chart and the velocity of the object as the height of the bar chart, okay? So at the very beginning, what did it say about the speeds of these graphs, or of these boxes? They're at rest. So how much, what's their velocity? Let me ask it that way. 0 in both cases, right? So for the first one, let's say that the mass of the box was, what was it, like 1? I don't remember. Something like this. And then was the second one the big one? Yes. Second one was the big one. So the mass is twice as big. So it's going to be twice as wide. Not that it really matters because it's just at 0. Okay? The initial momentum for each of the boxes is 0. Okay? Then what do we know about the force applied for box 1? Is it big or small? It's big. It's 3N, right? Or 3F. So let's make a little box for that, shall we? It's a little arbitrary because we don't really know how big. We don't know the numbers, but we know the relative sizes. So I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to cut it off there because I know that the other one has to be a third as big. So I'm going to add. So I've got a force of 3N, or 3F, I guess is really what it says. I just made it too wide because those are little tiny boxes. Does that seem okay? What's my other one going to look like? What's my other bar going to look like? How tall is it going to be relative to that one? What's that? A third of it. And so if we went up 9, then you're saying it's going to go up 3 boxes? Yeah. And how long are they pushing the second box for as compared to the first box? Same amount of time. So this one was too wide, so the other one's going to be too wide as well, okay? Friends, this is really just a graphical way to look at exactly the same thing that we spent the last couple days looking at. Okay? We okay? Is there a question? So the final momentum, so the initial momentum was 0. Let's look at this one. If I'm making that one too wide, I'm adding 0 plus, well, that's like 9 times 2 or 18 little boxes. So that means I get 18 little boxes. It's got to be too wide for 2 little widths of mass. 1, 2, I need to count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is mv initial plus some force acting over a time is going to give me mv final. Okay? mv initial plus a force times a time gives me mv final. This is the same thing that we said before. We just said it in a different way. We said F times T equals m delta V, or m V final minus V initial. But we could write this then as F times T is equal to m V final minus m V initial. See what I'm saying here? If I add this thing to both sides, this is really just mv initial plus a force times time gives me MV final. This graphical process is showing you the same thing as the impulse momentum theorem does algebraically. What's this other bar going to look like? How does the mass of box 1 compare to the mass of box 2? I couldn't hear. I heard somebody say something, but I couldn't hear. It's twice as big. So if the mass of box 1 is like 2 boxes wide, how much is the mass of box 2 going to be? How many boxes wide? 4 boxes wide? So I'm going to go ahead and just make myself 4 boxes wide. 1, 2, 3, 4. 1, 2, 3, 4. And if I've only got 1, 2, 3, I've got 6 boxes there. Did I do that right? I guess I kind of messed up my math because of the way that I did it. How high do I get to go? How high do I get to go? I have 6 boxes here. I have to go 4 wide. So like 2-ish, not quite 2, like a little less than 2. I can see really, really nicely graphically here that the velocity of this block, the box 1, is going to be a lot higher than the velocity of box 2. You can see it graphically right there. How are we doing, team? Are we okay? Is that making sense? Okay. I want you to put a note next to part F. We're going to skip part F for right now because we skipped something that they wanted us to do earlier and we didn't. So skip it. I want you to circle part G. And I would like you to work on that before you get here tomorrow. Does that sound okay? Okay. I would also like you, before I see you tomorrow, to try the next page, which is 5C. Okay? So before I see you tomorrow, I want you to do part G. So part G from, there's so many letters in this, page 5B, and do 5C. Okay? I want to pause now because I want to do a little story time with Miss Carbling. Okay? You will need a piece of paper out to write some notes down in just a second. I'm going to grab something here and then I will get started. 15 minutes for a story. All right, here it comes. Story time with Miss Carbling. Here it is. So I've got just a few minutes here, and in these few minutes, I'm totally going to rock it. It's going to be great. I'm going to tell you about my very least favorite Winter Olympic sport. Everybody guesses that. Everybody guesses that my least favorite Winter Olympic sport is curling, and you could not be more wrong. In fact, I love curling. Do you guys, have you ever watched curling? It is like the best. And there is so much good physics. There's friction, and there's momentum, and there are forces. And if you've never watched it, friends, holy cow, you should. So no, it's not curling. It is not. I love bobsledding. Like watching people fly down. No. What's that? No, that's awesome too. That's all that danger stuff. Winter snow? It is not. Like you're close. I like watching figure skating. Yeah! Woo! Yes. My least. Rarely does it happen that somebody guesses it so fast. My least favorite Winter Olympic sport is ice dancing. Now, what is that, right? So here's the thing. I want to be very, very clear that I have no skill at anything related to moving on ice. So I'm not judging, and if you are a future Olympic ice dancer, no offense intended, okay? Because I couldn't do it. But let me tell you why I don't really like ice dancing. So I like figure skating. I like figure skating like, individual figure skating because they can jump and they can turn and they can do all kinds of crazy cool stuff. I also like pairs figure skating because the great thing about pairs figure skating is that they can throw each other. Like there is a lot of risk and excitement when you get to throw people places on ice. The problem that I have with ice dancing is that unlike figure skating, my understanding, and I could be wrong, my understanding though is that the rule is that it's always in pairs and both partners have to have at least one skate on the ice at all times. Boring. The other thing that I have issues with when it comes to ice dancing, and this tells you a lot about me as a person. Okay, my husband always makes fun of me because whenever we're watching, especially like an action movie, and then there's like that like lovey-dovey crap at the end, excuse my language, that lovey-dovey stuff at the end, and you're like, really, we do not need this? I'm like, oh my gosh. Like, I like a good romantic comedy. I'm going to be honest. But like when they just throw it in at the, it's like, don't need it. Okay. So now you know a little bit more about me than you thought you might. And so then getting back to the ice dancing, here's the issue, is that every single time, 90% of the time, in ice dancing, what happens is that the two ice dancers are standing there, and they're like this. And they're gazing into each other's eyes. And I'm just like, come on. Like, really? Whatever. I mean, I don't really like it. Will you be my ice dancing partner for a second? Come stand right here for me, please. Thanks, Autumn. I appreciate you. Okay, so Autumn and I are going to be ice dancing partners. Okay? And so we don't have to gaze into each other's eyes because I don't like that part. But anyway, so we're going to stand there. We put our hands like this. Okay? And there's all this gazing into each other's eyes business that we're not going to do because we don't need that. But then the music starts, and what happens? What do they do? Do you know? Yeah, are you with me? And the one person goes this way, and the other one goes that way. Can you imagine this? Okay. Thank you very much for being my ice dancing partner. I so very much appreciate that. All right, so now we are going to figure out what's going on in all of that. So, again, why bring up the thing you hate, Miss Kay? Well, the reason is because even though I don't really enjoy watching it, it does have some good physics in it. Okay? So here we go. We're gonna tell this story. Now, I've been watching, everybody just watches the Olympics, right? And so you watch it, and so we're just gonna imagine that we're watching some ice dancing, and there are two people, and we're gonna call them, I don't know, let's call them Alice and Boris. Okay? And I like the name Boris because it just sounds awesome. I also, I don't know if you've noticed when you do problems, especially AP problems, that they always have one person with an A name. Have you ever noticed this? And one person with a B name? And there's a reason for that. Because the A and the B, right? Yeah. So anyway, we're talking about Alice and Boris. So we're going to draw a little free body diagram of Alice and Boris. You ready? So here it goes. So here is Alice. And here is Boris. Oops, I'm going to put them closer together so that they can, affect one another. So here we go. Oh, whoa. Come on. Something is going on. We'll try one more time. Stop it. Okay, we'll just go like that. All right, so tell me real quick, before any music starts, what forces are acting on Alice? Tell me what's acting on her. The force of gravity. And we're going fast because we don't have a lot of time. So I'm just going to go ahead and just call it FG. Forgive me, okay? FG. And then what else do we have? FN. And she's just standing there. And she's just standing there gazing into each other's eyes and all that goofiness, but they're just standing there, okay? And are there any other forces acting on her? Is there friction? Is there... So yeah, there's this, that's part of the reason that we love this too, right? Because it's frictionless, right? And the ice and all of that good stuff. Yeah, and so there we go, we got that. And then, talk to me about Boris. Same. FG. Talk to me. What did you say, Chris?
If their masses are different, the forces would not be the same.
Okay.
But
And
it's the same.
same direction, same names, but different things. Now, part of the reason that I enjoy doing this this conversation is because we get to own up to some stereotypes that we all kind of possess, right? So often when I say this, then I ask everybody, so who has a bigger mass? And your answer is going to be Boris, because you assume, right? Part of the reason I choose that name is because it sounds very big. But we don't know that Boris is larger than Alice. They might be the same size, or Alice might be really, really big compared to Boris. We don't know.
They are ice dancers.
They are ice dancers.
Probably isn't going to be the biggest.
We don't know. We don't know. I need to make a decision. Josh, you haven't said much lately, so I'm going to ask you, who's bigger, Alice or Boris? I don't care.
Let's say Alice.
Alice is bigger. So how is that? And it's all good, friends. We got to go because we don't have a lot of time. So what's that going to do to these pictures here?
Alice is going to have longer vectors.
Alice is going to have longer vectors. Let's make them longer. I'm just going to make just Boris's shorter just because of space. Is that okay? Am I allowed to do that?
Yeah.
Okay. All right. So there's FN and FG. All right. Sweet. So there we go. Now, that's not very interesting. The thing that's more interesting to me is once the music starts. Then the gazing into each other's eyes part is done. And there's another force that happens for Alice, right? What happens to Alice?
Force of Boris on Alice.
Boris is going to push on Alice. Do you agree?
I just did.
Yeah, there she goes. So this is the force of Boris on Alice. Are we doing okay? What effect does that have on Alice? She moves, right? Because now there's a net force, F net, in the x direction is just the force of Boris on Alice. And so that means that the mass of Alice times the acceleration of Alice has got to be something non-zero. You with me? And it's going that way. So that might be in the negative direction, we could say, because it's just back. I'm just going to put a negative down here just so we don't get confused. Now, that's all well and good for Alice. Tell me about Boris.
Force of Alice on Boris.
Does Alice apply a force to Boris? Yeah? Probably. I mean, you've all seen enough of this stuff to kind of have a sense of it, right? So we got a force this way. This is the force of Alice on Boris. Whoops, I was going to write his whole name out. Okay? And bless you. What does that mean about Boris? What's going to happen to Boris? He's going to accelerate as well. F net x for Boris is F of A on B, which is equal to the mass of Boris times the acceleration of Boris. Now I have 4 questions for you. We don't have a lot of time, so I want you to think about these questions and answer them as quickly as you can. Question number 1. Who pushes first? Number 2. Who pushes harder? Number 3. Who accelerates more? And number 4, actually 3 and 4 should switch, sorry. Boop, boop. Who pushes longer? Go ahead and answer those questions as fast as you can with your table mates. Go, 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 go. Bless you. Are you doing okay?
I'm doing so great.
Is there anything I can do to help you?
No.
Okay.
Well, are they going the same? Okay, I pushed harder. I pushed longer. We didn't have to cover.
I mean, a collective efficiency of Alice. Boris is not accelerating.
I know Boris is
Because Alice is bigger.
I'm gonna say who's just harder out. So the pushes
Boris just like
just first. Yeah. You're gonna make exactly what we do. Alice for Boris.
say? Come on. What's that? Which of these do you know the answers to, friends? Got an answer for one of them at least? What'd you say, Elena? What do you know?
Well, for number 3,
Uh-huh.
you accelerate 1 meters or so. I said Boris.
You said that Boris would accelerate more. Why? Does anybody else say Boris? Lower mass. And the lower mass means what? Higher acceleration. For what though? Like just in general? Like, I mean, we can go with that for now. I'm gonna ask more questions about it later. Tell me more. Tell me more. What else do you know? Do we know any others yet or not yet? Boris pushes longer. Why do you think? Say that one more time. I shouldn't hear what you said. Come back tomorrow. Come back tomorrow. I know, that's why you're going to come back tomorrow, right? It's like that cliffhanger. Now you have to come back tomorrow to find out the answers. I will see you guys then. Have an awesome day. I hope that